March 9, 1945. Tokyo, Japan. A column of B-29 Superfortresses crosses the coast at low altitude, their silver fuselages reflecting scattered moonlight over the dark Pacific. The lead pathfinders drop incendiary markers over eastern Tokyo, painting target boxes in chemical fire. Behind them, 334 bombers release approximately 1,665 tons of M69 incendiary clusters. Each cluster breaks apart at altitude, scattering dozens of 6-pound bomblets across the grid below. In the Shitamachi district, where wooden homes and paper-screened workshops stand wall-to-wall in neighborhoods centuries old, flame fronts merge within minutes into a firestorm that reaches temperatures near those of industrial kilns and creates its own winds. Survivors will describe hurricane-force gusts pulling people into the flames. By dawn, 16 square miles are burned out, roughly 87,000 dead, more than 1 million homeless, and 267,000 structures gone. American planners had expected high-altitude precision bombing to crack Japan's war industries. Jet stream dispersal and poor accuracy proved otherwise. The contrast is now stark. Low-level night incendiary attacks, centered on napalm, destroy more useful industrial area in hours than months of precision sorties ever achieved. In a single night, documented destruction exceeds that of any other air raid in history, signaling a strategy that will break Japan's capacity to resist. 3 years earlier, on the 4th of July, 1942, in Cambridge, Massachusetts, chemist Louis Frederick Fieser observed test pans flare on a workbench at Harvard University as a new gasoline thickener clung to metal surfaces and burned with steady intensity. Flamethrower fuels had been notoriously unreliable throughout the early war years, sputtering out within seconds or splashing harmlessly off targets, leaving assault troops exposed without effective fire support. Military requirements called for something fundamentally different, a substance that would adhere to any surface, burn longer and hotter, and remain stable during storage and transport. Fieser and his research team experimented with various compounds under contract from the Office of Scientific Research and Development. The aluminum salts of naphthenic and palmitic acids, combined in precise ratios through careful laboratory work, yielded a stable gel with properties that exceeded initial expectations. The gel demonstrated burn durations measured in minutes rather than seconds. It stuck to masonry, wood, and metal with tenacious adhesion. It could be ignited reliably by a small black powder charge packed into thin-walled bomblets. The viscosity allowed it to be pumped and handled like petroleum products while maintaining its incendiary characteristics. The OSRD classified the compound immediately under expedited wartime protocols and assigned it a name drawn from its chemical precursors, napalm, a contraction of naphthenic and palmitic. By late 1942, the U.S. Chemical Warfare Service recognized the strategic implications that extended far beyond tactical flamethrower applications. Napalm could be mass-produced cheaply using existing petroleum refining infrastructure. It could be stored safely for extended periods without degradation. It could be adapted for both flamethrowers and aerial bombs, offering unprecedented versatility. Industrial partners responded swiftly to military requirements. Standard Oil, DuPont, and Dow Chemical began converting existing plants and establishing new production lines to supply the gel. The Harvard Laboratory, initially a small academic research facility, became the coordination center for a nationwide classified project involving dozens of facilities. Chemical engineers worked to scale up batch processes that had been proven only in laboratory quantities. Quality control procedures were established to ensure consistency across multiple production sites. Transportation and storage protocols were developed to handle a substance that, while stable, remained inherently dangerous. By the war's end, the United States would manufacture more than 100,000 tons of napalm, transforming what began as academic chemical research into a strategic weapon that would reshape aerial warfare. The compound that started in test tubes would soon fill bomb casings by the hundreds of thousands. At Wright Field, Ohio, throughout the spring and summer of 1943, Army Air Forces, Materiel Command Engineers and Chemical Warfare Service liaisons conducted extensive dispersal tests. Ordnance officers weighed thin-walled casings, calculated ballistic properties, and observed how burning gel scattered through mock urban blocks constructed to replicate Japanese residential areas. The tests revealed critical insights. Early incendiary designs had fragmented poorly, with bomblets either failing to separate properly or dispersing in patterns too scattered to achieve sustained ignition. Clustered bomblets, however, delivered consistent coverage across target areas. Engineers studied ignition patterns, burn rates, and structural failure modes in different building types. They documented how napalm behaved when it struck different surfaces: wooden roofs, paper walls, tile, concrete. They measured temperatures, spread rates, and the time required for fire to transition from individual ignitions to merged conflagration. The data informed standardization efforts. The M47 and M69 incendiary clusters emerged from these tests as the primary weapons. The M69 became the workhorse of the incendiary campaign. Each M69 weighed approximately 6 pounds and contained napalm gel with an ejection charge and impact fuse. The bomblet was designed for simplicity and reliability. At a preset altitude, a clustered container would break open, scattering individual M69 bomblets across a wide area. Upon impact, each bomblet's casing would rupture, spreading burning gel that adhered to whatever it touched. Rack densities for B-29 bombers were calculated to maximize payload within weight and space constraints. A single B-29 could carry more than 1,500 bomblets in properly configured racks. The calculations showed that one aircraft load could seed ignition across several square city blocks, creating multiple simultaneous fires that would overwhelm firefighting capacity. The strategic implications were immediately apparent to planning staffs. Procurement schedules ramped rapidly with participating contractors across the United States. Standard Oil facilities in Bayonne, New Jersey, and Baton Rouge, Louisiana, converted refinery capacity to napalm production. DuPont plants in Delaware and West Virginia established production lines. Dow chemical facilities in Michigan joined the effort. By late 1944, monthly output surpassed several thousand tons and continued climbing. Quality inspectors verified batches. Transportation units moved drummed napalm from plants to coastal ports. Navy cargo vessels transported it across the Pacific to forward bases in the Marianas. The weapon was approved for combat deployment in the Pacific Theater with high priority designation. Industrial conversion aligned chemistry, metallurgy, and logistics to mass-produce incendiary clusters at unprecedented scale, turning laboratory experiments into munitions stockpiles measured in thousands of tons. Ordnance depots in the Marianas received steady shipments. Ground crews learned handling procedures. Loading procedures were standardized and drilled until they became routine. Few realized at the time that this new gel, born from academic research on a Massachusetts workbench, would soon destroy more urban area than both atomic bombs combined. By December 20th, 1944, mission assessments piled up on desks at North Field, Tinian, in the Mariana Islands. The reports made grim reading for strategic planners. High-altitude precision bombing missions against Japanese aircraft factories, bearing plants, and oil refineries were failing to achieve objectives. Bombs drifted miles off target in winter jet streams that forecasters had underestimated. Pre-war doctrine, developed in the clear skies over American test ranges, had promised pinpoint destruction of industrial targets from altitudes above 25,000 feet. Norden bombsight accuracy, proven in training and early combat, collapsed when confronted with winds exceeding 150 miles per hour and persistent cloud cover over the Japanese home islands. Strike photographs showed bombs scattered across countryside, hitting residential areas, fields, and waterways, while factories remained operational. Damage assessments compiled from reconnaissance photos and intercepted Japanese communications indicated that industrial output continued at levels unaffected by the bombing campaign. Aircraft production actually increased month over month despite the raids. The strategic problem was clear. the primary weapon system was not achieving its intended effect. General Curtis Emerson LeMay, newly appointed commander of the XXI Bomber Command in January 1945, faced a strategic impasse. A veteran of the European bombing campaign, LeMay had observed both the successes and limitations of strategic bombardment. Staff analysts presented him with urban construction data on Japanese cities, compiled from pre-war surveys, intelligence reports, and prisoner interrogations. The analysis revealed a fundamental vulnerability. Japanese urban cores were predominantly constructed of wood and paper. Centuries of tradition, earthquake engineering that favored flexible, lightweight structures, and economic factors had created cities that were inherently combustible. Typical residential areas consisted of single-story wooden homes with sliding paper screens, tile or thatched roofs, and minimal separation between structures. Industrial districts mixed factories with worker housing in dense patterns. Major cities had grown organically over centuries without modern fire breaks or comprehensive building codes. Staff analysts calculated ignition thresholds for various attack patterns. The numbers favored incendiaries overwhelmingly. A given tonnage of napalm incendiaries could ignite exponentially more area than the same tonnage of high explosives could physically destroy. Once multiple fires merged, a self-sustaining conflagration would develop that no civil defense system could control. Engineers demonstrated additional benefits. Removal of some defensive guns from B-29 seconds would allow increased bomb and fuel loads, extending effective range and increasing tonnage per sortie. Lower altitude attacks would reduce fuel consumption and improve accuracy while exploiting gaps in Japanese radar coverage and night fighter capabilities. LeMay reviewed the data and authorized a fundamental pivot in strategic doctrine. Command directives, issued in late February 1945, sanctioned low-level night area attacks using napalm clusters as the primary weapon. The decision represented abandonment of the precision bombing doctrine that had guided strategic planning throughout the war. Operational failure at altitude forced acknowledgement that a different approach was necessary. The most advanced bomber in the American arsenal, equipped with sophisticated navigation and fire control systems, would now employ the oldest battlefield element, fire, optimized by industrial chemistry. On the night of March 9, 1945, the new doctrine received its first large-scale test. 334 B-29 seconds assembled over the Marianas and set course for Tokyo. Pathfinder aircraft arrived first, marking target boxes over the Shitamachi district with incendiary markers that burned with distinctive colors visible to following waves. Winds funneled flames through narrow streets where densely packed neighborhoods offered continuous fuel loads. Each home shared walls with neighbors. Wooden structures stood mere feet apart. Paper screens and fabric furnishings provided additional combustible material. Japanese civil defense planners had anticipated scattered incendiary attacks, manageable by firefighting units and civilian bucket brigades. Pre-war planning assumed attacks would resemble traditional raids with mixed ordnance, creating scattered fires that could be isolated and suppressed. Saturation with napalm created conditions entirely different. Within minutes of the first bomblets striking, dozens of fires ignited simultaneously across square miles. Firefighting units responding to initial blazes found themselves surrounded by new ignitions. Water mains ruptured under pressure as multiple hydrants opened simultaneously. Pumper trucks found intersections blocked by fleeing civilians. XXI Bomber Command Pathfinder crews reported extraordinary visibility from altitude as the flames grew and merged. Individual fires combined into larger conflagrations. Superheated air rose in a column that drew surrounding air inward with increasing velocity. Tokyo Fire Brigade unit logs recorded water mains failing systematically as pipes burst from heat and pressure. Pump pressure collapsed as the water supply system exceeded its design capacity. Oxygen depletion was noted in enclosed streets, where fire consumed available air faster than circulation could replenish it. Temperatures in the heart of the firestorm reached levels that melted glass and ignited items normally considered fire-resistant. Post-strike reconnaissance photos taken at dawn on March 10 confirmed 200 67,000 buildings destroyed across 16 square miles. The flames had consumed industrial districts producing aircraft engines, precision bearings, and munitions alongside residential areas. Mixed-use zoning meant that machine shops, component factories, and home workshops were scattered throughout neighborhoods. All burned together. Casualties were estimated in official tallies at tens of thousands, with later analyses raising figures substantially higher. The concentrated application of napalm had overwhelmed civil defense capacity and destroyed industrial districts in a single operation spanning less than 3 hours of actual bombing. The glow remained visible to crews at long range as they returned to base, confirming the effectiveness of the low-level incendiary doctrine. Between March 11th and March 31st, after-action reports compiled at Guam Command Post showed results that exceeded planning estimates. Minimal losses relative to damage inflicted emerged as the defining characteristic. Low-altitude night raids had been expected to incur higher costs in aircraft and crew casualties. German defenses in Europe had proven lethal against low-altitude penetrations. Japanese capabilities, while degraded, still posed substantial threats in theory. Instead, actual losses remained comparatively low, while damage multiplied exponentially. 14 B-29 seconds were lost from all causes during the March 9th raid, a loss rate under 5%. Some losses resulted from mechanical failures rather than enemy action. Japanese night fighter response proved ineffective. Radar coverage had gaps. Fighter direction systems struggled with multiple low-altitude targets. Searchlight batteries, blinded by smoke and flames, could not illuminate targets for anti-aircraft guns. General LeMay and operations staff codified procedures based on initial results. Ground echelons adjusted loading and maintenance cycles to increase sortie rates. Crews stripped defensive guns systematically to maximize bomb loads. Navigation procedures for night low-altitude attacks were standardized. Target selection prioritized cities with maximum industrial value and combustible construction. Sortie generation rates climbed as procedures became routine. March raids burned major areas in Tokyo, Nagoya, Osaka, and Kobe in rapid succession. Command summaries recorded square miles destroyed across 4 major cities within 3 weeks, devastation that previous months of precision bombing had failed to achieve. A tactical doctrine became a repeatable campaign plan with established logistics and procedures. The same bomber force that had struggled to hit precision targets from altitude now destroyed more urban area per week than months of earlier raids combined. Through April and May of 1945, reconnaissance mosaics pinned to operations room walls at headquarters showed burned grids progressively replacing factory wards across central Honshu. Photo interpreters marked destroyed areas in red on master maps. The red zones expanded with each mission. Intelligence analysts compiled damage assessments from multiple sources. Planners had expected partial impairment of industrial capacity disruption and delay rather than complete elimination. Production reports compiled from intercepted communications and prisoner interrogations showed something far more severe, approaching near collapse in critical sectors. Aircraft production figures dropped sharply. Plants producing engines, airframes, and components either burned completely or suffered damage that halted operations. Bearings manufacture, critical for all machinery, showed particularly steep declines. Electrical components production fell off steeply as plants, and the electrical grid itself suffered repeated damage. Japanese municipal officials logged displacement figures that climbed into millions as urban populations fled to countryside areas. USAAF photo interpreters quantified damage methodically, measuring destroyed areas, counting collapsed structures, noting changes between successive reconnaissance passes. Documented multi-square-mile burnouts accumulated across target cities. Industrial output reductions, measured in double-digit percentages, appeared in intelligence summaries. Port throughput declined as dock facilities burned and cargo handling equipment was destroyed. Rail yards suffered repeated strikes that cratered tracks, burned rolling stock, and destroyed switching facilities. Japanese Home Ministry and Cabinet reports, intercepted through signals intelligence, admitted production paralysis in key sectors. Internal government communications acknowledged situations that public statements denied. Repeated napalm raids, severed supply chains, and labor pools simultaneously. Factories that survived physically could not operate without components from destroyed suppliers. Workers displaced from burned residential areas could not reach surviving workplaces. Transportation networks, already strained, broke down under the cumulative damage. By late May, multiple metropolitan areas functioned as shells, addresses, and street grids remained on maps, while the actual industrial activity had ceased. Production existed only on paper in many sectors. At Harmon Field, Guam, ordnance crews maintained the logistics pipeline that sustained the offensive. They stirred napalm gel in 55-gallon drums, mixing compounds according to standardized recipes and filling bomb casings in assembly line fashion. Cargo manifests tracked chemicals by the ton flowing through supply depots. Each B-29 sortie consumed approximately 7,000 gallons of aviation, gasoline, plus oil, munitions, spare parts, and the bombs themselves. Bomb-to-shipping ratios were calculated carefully to optimize cargo space on transport vessels. More than 25 U.S. plants supplied gelling agents and fillers to forward bases. The supply chain stretched from refineries and chemical plants in the continental United States across the Pacific to island depots. Cost per pound of napalm proved substantially cheaper than TNT or other conventional explosives, an important consideration given the tonnages involved. Critics within military planning circles had warned that fuel requirements, shipping capacity, and maintenance demands would limit sustained incendiary operations. Available infrastructure would prove inadequate for extended campaigns, they argued. Sortie counts continued to rise, proving the pessimists wrong. Navy convoy planners coordinated shipping schedules that kept supplies flowing. Depot chemists maintained quality control over stored munitions. Mechanics kept aircraft operational despite intensive flying schedules. A resilient logistics web converted American petroleum production and industrial capacity into urban destruction thousands of miles from the continental United States. Movement and consumption logs documented that the pipeline could sustain over 1,000 sorties weekly theater-wide for extended periods. The supply system proved robust enough to support operations at scales previously considered impossible. In the ledger of total war, the arithmetic was brutally simple. 1 drum of gel, properly employed, equaled city blocks of factory roofs ignited. Tonnage delivered translated directly into square miles burned. The industrial capacity that had seemed overwhelming to earlier planners proved adequate once properly organized and directed. By late June and into July of 1945, intercept plots on Japanese air defense operations boards at monitoring stations showed patterns that confirmed systematic collapse. Plots thinned progressively as operational radar sets and available fuel stocks dwindled to fractions of earlier levels. Defense planners in Tokyo had expected to attrit American bomber streams through concentrated fighter response and anti-aircraft fire. The strategy required functioning radar for early warning and intercept direction, available fuel for fighter operations, and trained pilots to fly missions. All three elements eroded simultaneously under the cumulative pressure of the campaign. Documented fighter sorties fell sharply, month over month. Missions that once generated hundreds of sorties now produced dozens. Anti-aircraft effectiveness, measured in bombers destroyed per raid, remained consistently under 1%, statistically insignificant against formations numbering hundreds of aircraft. Japanese air defense commanders noted fuel and airframe shortages in situation reports. Both resulted partly from direct bombing damage and partly from the disruption of production and transportation networks. USAAF intelligence sections aggregated intercept data, showing the breakdown in detail. Radar station outages increased as equipment failures went unrepaired. Maintenance parts became unavailable. Power supplies failed. Aviation gasoline scarcity reached critical levels as refineries burned and transportation systems broke down. Declining pilot availability reflected both combat losses and the collapse of training programs that required fuel and aircraft. Rail disruption hindered redeployment of units from one threatened sector to another. Commands could not shift forces to meet attacks. Cabinet minutes intercepted through signals intelligence conceded that the home front could not sustain continued bombing at current rates. Internal government assessments acknowledged realities that public statements denied. The napalm raids degraded not only cities but the means to defend them, creating a compounding collapse where each raid made subsequent raids easier. With defenses failing systematically, even medium-sized cities with modest industrial value became viable targets for complete destruction. On the night of August 1, 1945, Toyama received attention as a demonstration of what systematic application of incendiary warfare could achieve against an essentially undefended target. A concentrated stream of B-29 seconds lined out over the darkened coastal grid, where the city's aluminum smelting and ordnance plants sat within predominantly wooden wards. The city, medium-sized by Japanese standards, with perhaps 125,000 residents, had been expected to survive partial damage as a less critical target. Intelligence assessments rated it as possessing some strategic value, but not justifying the same priority as major metropolitan centers. Post-strike surveys recorded approximately 99.5% urban destruction, the highest documented percentage of any city targeted during the entire war. More than 173 B-29 seconds dropped approximately 1,700 tons of incendiaries across the target area over a period of just over 1 hour. The result approached total annihilation. Near-complete loss of urban footprint and productive capacity followed. Reconnaissance photos showed virtually nothing standing in the burned area. Streets remained as geographical features, but structures had vanished. XXI Bomber Command mission leaders documented results with precision. Toyama municipal staff, who survived, documented loss for their records. U.S. mission reports, filed as part of routine after-action analysis, declared matter-of-factly that Toyama had ceased to exist as an industrial entity. The phrasing, bureaucratic and clinical, captured a reality almost unprecedented in warfare, an entire city effectively erased in a single operation. The erasure of Toyama confirmed that by summer 1945, tactical outcomes no longer depended on defenses, terrain, or weather. Logistics and chemistry determined results. Given sufficient ordnance, navigation to target, and combustible urban fabric, a city could be removed from the Japanese war economy overnight with near certainty. In early August, parallel operations proceeded on Tinian's crowded airfields. On one ramp, standard bombardment groups loaded clustered incendiaries for routine missions against targets up and down the Japanese archipelago. Crews followed established procedures, checked standardized loading configurations, and filed flight plans for low-altitude night strikes that had become commonplace. The missions represented continuity execution of a campaign plan that was systematically destroying Japan's urban industrial base. On another ramp, isolated behind security perimeters and restricted areas, a specially modified B-29 from the 509th Composite Group prepared to depart with an entirely different weapon. The preparations attracted notice even among personnel not briefed on specifics. The level of security, the presence of unfamiliar personnel, and the obvious special handling indicated something unusual. Public memory in subsequent decades would link Japanese surrender almost exclusively to atomic shock, the devastating psychological and physical impact of nuclear weapons employed against Hiroshima and Nagasaki. The narrative of instant, apocalyptic destruction ending the war became the dominant historical interpretation. Contemporaneous USAAF forecasts told a different story. Staff analyses predicted Japan's urban industrial collapse within 30 days, based purely on cumulative incendiary attrition, independent of any atomic deployment. The projections assumed continuation of current sortie rates and targeting priorities. By August 5th, more than 40 cities had been heavily burned, with damage ranging from 30% to near total destruction. Ongoing incendiary plans documented at command headquarters listed dozens of additional targets across the home islands. The target list included every city with meaningful industrial capacity that had not yet been struck. Internal memos circulated among planning staff assessed surrender likelihood based on cumulative urban destruction, food supply disruption, and industrial paralysis. The assessments concluded that continuation of the incendiary campaign at current intensity would force capitulation regardless of other factors. The Napalm campaign had established a strategic baseline of systematic destruction that made Japan's military-industrial defeat inevitable. Atomic strikes would accelerate an already terminal decline and provide a face-saving rationale for surrender, but the underlying cause of defeat had already been established. Even as nuclear history began on August 6th with Hiroshima, the nightly gel-fire war did not pause. Standard bombardment groups continued loading incendiaries and flying missions. Target folders remained stacked for execution. The campaign machinery continued operating. Between August 10th and August 14th, as Japanese government deliberations moved toward surrender, photomosaics quantified the scope of destruction across Tokyo and other major cities. Intelligence staffs compiled damage assessments from accumulated reconnaissance data. Ministries in Tokyo tabulated displaced civilians, approaching 9 million across the country. They calculated lost electrical generating capacity, lost kilowatt-hours of production capacity, disrupted transportation networks, and collapsed supply chains. The government had assumed that dispersed industry and home workshop production could survive aerial attacks through distribution and concealment. Modern centralized factories might burn, but traditional distributed production would continue. The data showed that assumption was wrong. Electrical output had fallen more than 60% from peak levels. Without electricity, home workshops could not operate machinery. Steel production had collapsed more than 80%. Without steel, no manufacturing sector could function. Rail movement was heavily impaired by damaged infrastructure, destroyed rolling stock, and fuel shortages. Without transportation, no distribution system could operate. Imperial General Headquarters, staff officers, and Home Ministry compilers of civil defense and production statistics confronted aggregate figures that told an unambiguous story. Approximately 106 square miles of more than 60 cities had burned. 2.5 million buildings were destroyed, representing enormous loss of productive capacity, housing stock, and public infrastructure. Millions remained homeless, straining food and shelter resources. Council notes from meetings during those final days acknowledged explicitly that continuing resistance was no longer sustainable. The industrial base necessary to support military operations had been eliminated. Administrative recognition of strategic insolvency preceded the actual surrender broadcast. The Emperor's decision to accept Allied terms came after the destruction was already complete. The Empire yielded while its urban map was already a ledger of ash, with red zones of destruction covering the areas that had once held Japan's industrial might. 1 year later, in October 1946, 2 separate processes of documentation were underway on opposite sides of the Pacific. In Washington, D.C., the U.S. Strategic Bombing Survey bound its multi-volume analysis of the Japan air campaign. Teams of analysts had spent months in Japan examining records, interviewing officials, surveying damage, and compiling statistics. The resulting volumes represented the most comprehensive assessment of strategic bombardment effects ever undertaken. In Tokyo, museums and archives began the process of preserving artifacts and documentation of the air raids. Fire department facilities displayed melted equipment pumps deformed by heat, helmets fused by temperatures that exceeded metal's melting point, hoses that had burst when water boiled inside them. Many observers, both military and civilian, had expected atomic weapons to dominate casualty and destruction statistics. The sheer power of nuclear weapons and the dramatic nature of their employment suggested they would overshadow conventional attacks. Compiled analyses from multiple sources showed a different picture. Napalm and incendiary raids had killed more people in aggregate during the final campaign months than the atomic bombings. The total from conventional incendiary attacks exceeded combined Hiroshima and Nagasaki casualties by substantial margins. USSBS analysts and Tokyo Fire Department curators documented results with methodical precision. Approximately 100 to 6 square miles of urban area destroyed by incendiary attack, 500,000 fatalities attributed directly to incendiary campaigns over the 6-month period from March through August 1945. More than 40,000 tons of napalm dropped during spring and summer, not counting earlier uses or other incendiary types. 2.5 million homes destroyed, displacing approximately 9 million people. The Strategic Bombing Survey reached an unqualified conclusion, stated plainly in its summary volumes. Urban Japan's production system had ceased to exist as an organized whole by August 1945. The phrasing was technical and bureaucratic, but the meaning was clear. Japan's industrial economy, built over decades of modernization, had been systematically destroyed in approximately 6 months of sustained incendiary attack. Incendiary warfare, cheap relative to other options and mass-producible using existing industrial infrastructure, had proved decisive against combustible urban construction. The cost-effectiveness particularly impressed analysts. Napalm had cost roughly 38 cents per pound to produce, substantially less than high explosives. Transportation costs were comparable, yet the destructive effect per ton delivered had been orders of magnitude higher against the wood and paper construction that characterized Japanese cities. The economic arithmetic of the campaign showed extraordinary return on investment in purely military-industrial terms. The deadliest single raid of the war, analysts noted, had not been nuclear. Tokyo on March 9-10 exceeded both atomic bombings in immediate casualties and approached their totals in long-term effects. That fact, documented thoroughly in official records, would be largely forgotten in subsequent popular understanding of the war's end. Napalm remained in production in substantial quantities long after 1945. Stockpiles were maintained. Production capacity was preserved in ready reserve. The substance was employed in Korea from 1950 through 1953, in Vietnam extensively from the early 1960s through 1973, and in other conflicts where U.S. forces operated. But public reaction and international perception changed dramatically from the war years. Images from later wars, particularly Vietnam, transformed public perception from efficient area weapon to symbol of civilian suffering and indiscriminate destruction. Photographs of burned civilians, especially children, created associations that were absent from World War II coverage. Wartime staff in the 1940s had framed napalm use as strictly military efficiency, tonnage calculations, target coverage, cost-effectiveness. Post-war discourse, particularly from the 1960s forward, centered increasingly on humanitarian concerns and questions of legal constraint under emerging international law. U.S. procurement officials continued to defend napalm as a legitimate military tool with specific tactical applications. Later-era journalists investigated its effects and uses. Veterans from various conflicts described their experiences with the weapon, both as users and as witnesses to its effects. The accounts varied widely. Some emphasized military effectiveness in specific tactical situations. Others expressed moral qualms about its employment. International critiques grew in volume and intensity, particularly during the Vietnam era. Official military reports retained the 1945 conclusion about effectiveness against combustible urban targets and dense vegetation. The technical assessment never changed. Napalm remained highly effective for its intended purposes. But international opinion, codified partially in treaties and protocols developed through the United Nations and other bodies, moved toward restricting or prohibiting its use against civilian populations. The debate continued. The 1945 campaign remained historical fact. It had closed the Pacific War through systematic application of chemistry and logistics, demonstrating that industrial capacity properly focused could overwhelm even a determined enemy. But the legacy remained contested. Questions persisted about whether area attacks on cities constituted legitimate warfare or crossed lines that should not have been crossed even in total war. The arguments continued decades later with no clear resolution. By August 15, 1945, Japan's surrender came after months in which cities were progressively rendered non-functional, not primarily through the physics of the atom, though atomic weapons provided the final shock. but through barrels of napalm gel and the vast industrial systems that produced, transported, and delivered them across thousands of miles of ocean to burn the urban industrial heart from an empire. What is your perspective on this part of history? Share your thoughts in the comments because every memory and reflection helps keep the past alive.